Let's do a quick example of the Gauss-Seidel iterative solution method. I've gone ahead and entered the A matrix in this example. And if you note, each A matrix has, by design of the textbook, I'm sure, a very dominant diagonal term. In each row, the diagonal term in this example is larger than the combined absolute values of the off-diagonal elements. So 4 is greater than 0 plus 1 plus 0 plus 1. Yep, 4 is greater than 2. 5 is greater than 2 plus 1 plus 1. 3 is greater than 1 plus 1. So in every row, it works out. I need to enter in the solution vector since we actually are doing an iterative method here. So I need to do that as a column. 32, 19, 14, negative 2, 41. Okay. Keep in mind that if you entered it the wrong way, you can always say B prime, and that translates it. So B prime in that case is not actually prime. Sorry, it's an apostrophe. That represents the transpose. Doesn't change it permanently unless you set the reassignment variable to do so. All right, let's clear up that screen and start discussing what the code is going to do. If you haven't yet watched the video discussing the progression of the Gauss-Seidel method, it first moves everything into an explicit form so you can solve for the x values of each row. As is tradition in these matrix methods, we start by saving the size, the number of rows, and the number of columns into their respective variables. And in this case, I initialize a solution vector, only one column. I went ahead and set explicitly 1, so that way it would be a reminder, of size the number of columns. So I start count at 0 because count is going to be the number of iterations. That was actually the last thing I put in. I got one iteration working, an iteration being that code between lines 9 and 21 I highlighted. And then at the very last thing, I started the code cycling. So it updated itself in progressively more accurate iterations. So right now I had it set to do maximum of 5, whatever. Change it to 1 for the moment. So let's look at what the actual update cycle looks like. So we start with for I equals 1 to R. So I will be our row index. X is already equal to B. Now, that's interesting because now we're doing the summation one row at a time because we're solving each row for its explicit form. So if I can go back and remind you again about explicit form, here it is in the document camera. We are solving an input given to us in this format where A11 times X1, A12 times X2, so on and so forth, general form for a matrix. We're solving it for the diagonal variable equals the solution minus all of the other stuff in that row, quantity, in square brackets, you see, divided by A11. So, back in the window, you have the solution for the row, and then we procedurally go from the left to the right on the row, subtracting the value, here it is, subtracting A of ij times X of j. So, A of the row we're on, the position we're cycling through, times the x variable of the position we're cycling through, except there's one we want to leave out intentionally. We want to leave out the diagonal term because that's the one we're trying to solve for. So look, that's why the if statement makes an appearance. And actually, I realize I could have done this a simpler, shorter way after making it, but yeah, sometimes you don't have to be efficient, it just has to work. If I equals j, that means if you're on the diagonal, if your indices match, A11, A22, A33, A44, etc., do nothing. Do not add that term to the existing value of x. Else, so in the case where that is not true, which is actually the shortening I could do the not equals and then get rid of a few lines, and things can happen. Improvements can be made. If you're not on the diagonal, then it does go ahead and add the coefficient multiplied by the appropriate value of x. I say add because it's adding these contributions, but in this case it's subtracting. It's combining. Go ahead and combine a times the appropriate x value into the already existing value of x. And at the very, very end, after you've done all of the row operations, all the column cycling in a particular row operation, notice J is columns, and we've just finished a loop through the different columns. The last thing you do before going into the next row is divide that total numerator, which you now have all the terms for, divided by A of II. So the diagonal term that you skipped over with this if statement, you skipped it because you have to divide by its coefficient to solve for x of I. So if you look again at, I guess that would be figure 421 on page 132 of your textbook in the 3rd edition, you would find the equation that we're mimicking here, doing it one row at a time. And that would be one update. In the process of forming all these terms, you've gone ahead and updated the equations. In fact, you've done this in the Gauss-Seidel iterative method because you're already using, by default, the newest values of xi. Actually, that's the final formulation there because you're dividing by a ii. Whenever you start doing the next row, so whenever I shifts to a value of 2 instead of 1, it will use the updated value of x1 that you did in the previous step. So, you actually did the more advanced method in the easier way. So let's run this and stop talking and let's see here. So this would be Gauss-Seidel iterative inputs of A and B. Hopefully nothing breaks. Let's see. Looking okay so far. All right, so 8.62, negative 0.65, and 7. That's one iteration. This is not going to be the converged solution. Oh, right. I have it set to do one iteration. Let's change this to 5. Run it again. Whoop. There we go. Now every time I press spacebar, it's going to go on from the pause value. So the second iteration looks thusly, third iteration, fourth, fifth. And then it's done. So right now it looks like it's approaching a value of 5, 2, 4, 3, and 8. Let's see if that's right. Let's do this the built-in way. A inverse times B, 5, 4, 2, 4, 3, 8. Oh, 5, 2, 4, 3, 8. Yeah, 5, 2, 4, 3. So it looks like it's converging, but we need to get more accuracy. So as you might expect, we would just go into this code. Instead of just doing it a maximum of 5 times, let's do it 15, see how much closer it gets. In fact, let's take this pause out so it'll just do it, not wait for us to press spacebar. So you see it's approaching. That's kind of the nuisance part of iterative methods. It's like it always edges closer and closer and closer to the value. It's almost like it's taking the limit. Because you have to run these things a lot of times before the round-off error gets small. In practical terms, look, I mean, we are at how many decimal places? 1, 2, 3, 4, 5, 6. So you're fine. I think you should feel very confident in saying that is a 2, that is a 4, that is a 3, that is an 8. But the option still exists. Just invert, multiply, and then you get a much nicer integer-type solution. Real world doesn't generate integers very often, so you should be fine. But that is a quick walkthrough of the Gauss-Seidel iterative method, as well as an example. That was example problem 416, by the way, if you wanted to follow through, and it does line up. You have video with the code to make this function right in front of you, so happy homeworking.